So we're first asked to describe the trend, and we want it since 2009. So looking at this, we've got 2009. So from 2009 it drops a little bit, but on the whole is increasing. So describing the trend is increasing. Okay, and calculate the number of vehicles registered. So we're looking at all of the vehicles registered in the third quarter of 2002. So we know from the data sheet that since 2002 it's dropped by 2%. So if we set 2002 as 100% and 2015, if it's dropped by 2%, then we'll be down to 98%. Now, on our data sheet, it tells us that 876,000 vehicles were registered. So we've got 876,000. Now, 2015 is worth 98%. So if we are not so confident with percentages, we can do this as 876,000 divide by 98 to get 1%, and then times by 100 to get the 100%. If we're more confident with percentages, then we can use a percentage multiplier. So to go from 100 to 98, we would times by 0.98. So going back in time, we will divide by 0.98, and we would expect this to have increased, and we've got a value of 893,877. And here we've got a decimal, so we are looking at effectively half a car. So instead of our final one, we would round that up, and if we were doing it to 3 significant figures, which is what we're normally asked for, okay, so if we want to calculate percentage change in the number of new vehicles between 2002 and 2014, we know from part B that 2002 to 2015, the old version is 100%, and then it decreases by 2%. So we've also got 2014, which would be our original value, going to 2015. So 2014 to 2015, we are told that it increases by 8%. So this would be 108%. So if we want to get from 2002 to 2014, our first jump takes us to 98, and then we need to go back to 2014. So for that, we would divide by 108 and times by 100, which is the same as dividing by 1.08. So our percentage change is going to be 98 divided by 1.08. So that gives us 90.7. So if we go from 2002 to 2014, that actually ends up as going from 100% to 90.7. So our percentage change is going to be the difference between those two. So we have decreased by 7.26%. So we've got a percentage change of 9.26%. Okay, so one part D, we want the number of motorbikes in 2015. So looking at our data sheet, motorbikes are at 4%, and our total vehicles, we're also told, is 876,000. So in order to work this out, we are going to have to find 876,000 and divide that by 100 and times it by 4 to get 4%. 100 times by 4% equals 35040 motorbikes. Okay, we are then asked for the number of buses as a proportion of other new vehicles. So on our data sheet, we've got other vehicles, and we have buses at 0.3. So as a proportion, we can work this out. So we've got buses and we've got other vehicles. So our other vehicles are 18.7%. Our buses is 0.3. So to work that as a ratio, we can do 18.7 divided by 0.3 gives us a ratio of 1 to 62.3 reoccurring. So for every one bus there are 62.3 other vehicles. Okay, section B with the UK Snooker Championship. Which of the point scores could be considered to be outliers? Now, an outlier is something that is further than 2 standard deviations away from the mean. So we are told that we have a mean of 59.7 and a standard deviation of 39.2. So we are looking at 59.7 plus 2 lots of 39.2. So if we go to the menu, 59.7 plus 2 lots of 39.2. So an outlier would be anything over 138.1. 130.1. So looking at his scores, we have 151, but that is the only outlier. So we've got 151 is an outlier because it lies more than 2 away from the mean. Okay, so Neil Robertson was also in the final in 2013, and we're given the points scored by each frame in the match. So we're then asked to calculate the mean and the standard deviation of the points in 2013. So for that we need to go into stats. So we've got 1 and 76, 10, 0, 22, 39, 65, 1, 2, 3, 22, 101, 122, 132, 71, 61, 0, 59 and 82. Now it tells us that we had 17 frames, so a very quick and sensible check is that you've got 17 numbers. We are then going to calculate. If we check our settings, we've put stuff in list 1 and there's only one of each thing. So we go into one variable and it gives us the mean at the top and our standard deviation. So we've got a mean of 58 and we have a standard deviation of 43.39. So compare the standard. So we are looking to compare, and we've got to do the mean and the standard deviation, and we have to do it in context. So we've got the mean and standard deviation from the 2015, which we're given on the data sheet. We've got a mean and standard deviation that we've just worked out from 2013. So, comparing in context, in 2015 the mean is higher, so the 2015 mean is higher, and this suggests that he scored more points per frame. And then for the standard deviation in 2015 was 39.2. Here we've got 43.39. So the 2015 39 and 43. So the 2015 standard deviation is smaller, which suggests he is more consistent.
I've never seen that before. I've never seen every contestant pick the same option. I think it made for a fascinating day.
In his scores. So, important things. You've got to make sure you refer to the mean, you've got to refer to the standard deviation, you've got to compare the two things from the 2 years, and you have to put it in context. Right, so we are looking to find the correlation coefficient between the recorded number of snowshoe hare and lynx pelts obtained by trackers between 1880 and 1900. So from a datasheet point of view, that's going to be 1881 is the first thing that comes into this heading, and 1900. So we are going to have to take 1899. So we need to make sure that when we enter this into our calculator, we've got the hares in our X column and the lynx in our Y column. It's important that they are done in their pairs, because what we need to find out is the relationship, so the linear relationship between the number of bunnies, so the number of hares, and also the number, what have I got to? 83, that'll be 18, not 13. So the fact that you've got them in their correct pairs is really important. 15. So we're looking at comparing two variables at different times. So really obvious first check is that you have the same number of things in both columns. Your setup should have list 1 and list 2. This is a thing, your 2 variable stuff you don't ever have to change. So to find out your correlation coefficient, that's talking about a relationship and is your regression. And we are looking at a linear relationship, so we use X. And we normally use Y equals MX plus C. So the options we've got will go with AX plus B. So we get given a whole load of information. And so the bit we need is R. Correlation, regression, relationships. They've got the thing they've got in common is the R. So explain your answer in context. We've got 3A. So R is equal to 0.944. So what we've got here is really strong correlation. So this tells us that the relationship between the number of links between the links and hares is a strong linear relationship. So the closer the value is to 1 or to -1, the stronger the linear relationship. The closer it is to 0, the less relationship you've got. So find the equation of the regression line. So equation of the regression line, we're already on the right bit of the calculator. So we've got 3b is y equals, it tells us at the bottom that we're doing ax plus b, so y equals 0.414x plus, then b is 14.2. And it then asks us to draw this line on the scatter graph. When we are drawing a line of best fit, there are a couple of points that we have to make sure that we put on. First off, if we go into 2 variable, we can find out what x bar is. So that's the mean of our hairs. And we need to know what the mean for our links is. So if we scroll down, we've got 34.8. So we have to plot this point. It is good practice to plot 2 other points. So looking at our graph, if we first off plot 49.8 on our hairs and then 34.8 on our links, so we're going up in 2s for each thing. So our x is tiny bit below 50 and our y is tiny bit below 35. So we've got this one, which is our mean. If we look at our equation, then we've got our y-intercept at 14.2. So 14.2, if we go up to 14, and then we've got a little bit. And then in an ideal world, we want something over here so that we can just double check how accurate we are. So if we substitute in, if it goes roughly speaking there-ish, if we substitute in 150, then we get 0.414 brackets, if we use 150 for our x, plus 14.2 is 76.3. So we've used 150 with 76.3. So 76.3 is going to be about there. The reason for doing 3 points rather than 2 is if you have screwed up one of them, it's really obvious. So if you've plotted one not in the right place, you'll find that you do not get a line. So looking at this, I've got something that's not quite right. So double checking time. We are slightly below 50 and our other mean is 49.8. So 49.8 and 34.8. So 34.8. 1, 2, is actually going to be a tiny bit higher, which hopefully now we've checked. And this is why you draw graphs in pencil. Sadly, pencils don't show up quite as well on a camera. So, which point could be considered an outlier? So, our point that could be considered an outlier, and that was at 14.2. So, outliers. An outlier is something that is far away from our line of best fit. So, two things that could potentially be outliers. We've got these ones, but from looking at it, I would probably go with this one is the furthest from the line. So the outlier that we potentially have here from 3BII, if you are not completely convinced that you can identify it, read it straight off, then you've always got the original table. So we are looking for two that are about on 18. So we've got one at 35 and one at 26. So that will be the one at 35. So our outlier, if it's going to be anything, is going to be 1835. And that one has the potential for an outlier because it's the furthest from our line of best fit. Okay, so use your regression line to predict the number of, so we are predicting links when 100,000 hair pelts were obtained. So we've got our hairs are our X's, so we have 100,000. We need to be a little bit careful because what we have is things in thousands, so the number that we're putting in is going to be 100. So we've got BIII, and so we have X equals 100 because we have 100,000 snowshoe hairs, and we have our equation. So we need to evidence that we know how to substitute in. So we've got y equals 0.414 brackets 100. So this is our substitution, plus 14.2. And that's going to give us an answer of 414 plus 0.2.
How do you cook at home?
Really loving it. Certification, what that's as much size as I can really.
Couldn't you make space for us here today?
Let's actually put this in properly. 414 brackets 100 plus 14.2 is 55.6. So that sounds just about reasonable on the basis that actually if we're looking at something that's about 100, we've got something in the region of 50 to 60. Comment on the reliability of your prediction. So, our prediction's actually pretty reliable. And it's reliable because 100 hairs is within the data set. So 100,000 hairs is within the data set, and we've got a strong positive correlation. and has a strong positive correlation. So is reliable. Right, so fetal growth. We know that this is a normal distribution. We know that it's weight. And we know that we're mostly talking about a 10% and 90%. And that's pretty much all the information that we're given about the fetuses on the data sheet. So we are looking at the estimated weight at 28 weeks. It may be assumed to follow a normal distribution, which means we can use a normal distribution. We have a mean of 1.21 kilograms and a standard deviation of 0.16. So we've been asked to calculate a percentage, so not a probability, a percentage, who would have an estimated weight of more than 1.3. So things we need to identify. We've got 4A. We need to know what the mean is. So the mean is 1.21. The standard deviation is 0.16. We don't know our probability, but we do know that our number in context is 1.3, and we are looking at more than. So we start off with the probability that big X, which is the number in context, and hopefully context has an X in it, is more than 1.3, and that equals the probability that Z is more than. So to calculate Z, you do X minus mu divided by sigma. So on a calculator, we are doing a stats paper. So if we go into stats, we want a distribution that is normal, and we want the middle one. So if it's more than, then this is going to be a lower bound. So lower bound is 1.3, upper bound is something big. Standard deviation is 0.16, and the mean is 1.21. So this is our lower bound. So we also need to put a lower bound in for our Z value, and our lower bound is 0.5625. We've got a probability, and our probability is 0.2869 to 4 decimal places. Okay, because this is less than 0.5, we also have to write a line that says 1 minus probability Z, and we flip this sign 0.5625. We only put this line in if our probability is less than 0.5, and then we were asked for a percentage, so that's going to be 28.69%. Okay, for our second question, we've been asked to calculate the percentage. We are still doing a 28-week fetus, and we want a weight between these two values. So our mean is staying the same, our standard deviation is staying the same. So for B, we have a mean of 1.21. We have a standard deviation of 0.16. We don't know our probability, and we have two values in context, 1 and 1.4. So we need to calculate the probability that x is between 1 and 1.4. So for that we need to calculate the probability that z is 1 minus the mean over the standard deviation is less than or equal to z less than or equal to 1.4, take the mean over the standard deviation. So from a calculator point of view, you will find that it keeps your mean and standard deviation unless you've changed it. So we've got a lower value, a lower bound, and we've got an upper bound, and we want to know what it is between. So we are given our z values, so we've got the probability that z minus 1.3125 less than or equal to z less than or equal to 1.875, and that gives us the probability of 0.7878, and we are asked for a percentage. So if we're asked for a percentage, that's going to be 78.78%. Okay, so we've been asked to find the 90th percentile. So that's 90% or 0.9 for a fetus, still 28 weeks, and hence state the normal range of weights. So when we work out the range of weights, we need to find out between our 10% and our 90%. So we still know our mean and our standard deviation. So for C, we've still got the same mean and we've still got the same standard deviation. And we know that our probability is going to need to be 0.1 and 0.9, and we don't know our value of x, either of them. This is because, so we've got to find 10% and 90% because we are told that above 90% fetus is between 10 and 90% fetus is normal, over 90 is large, under 10 is small. So because we don't know our number in context, we have to go into distribution normal inverse, what you'll find is it keeps the previous information that you've got. So I need, for this, we've got our normal distribution, so we need to find these two things. So we've got two ways of doing it. Because this is 10% and this is 10%, this bit in the middle is 80%. So if we are just doing the bit in the middle, then we've got a centre, we've got 0.8, we've got our mean and our standard deviation, and it gives us two values. Our upper bound should be 1.41, and our lower bound is going to be 1. So, things that we need to write. So, we know that if it is in context, then we have 1.005 is less than context is less than or equal to 1.415. We also, if we want to find our Z values, what we can do is we can change our standard deviation to 1 and our mean to 0. At that point, we can do the probability for Z, which is minus 1.28 is less than or equal to Z is less than or equal to 1.28. We officially need to work out how to get our value of X. So what we can do is put in or substitute into our equation. So we've got Z equals X minus the mean divided by the standard deviation, and that will give us a value of X, which we actually found out first. You can also do this for the higher value. So we've got X minus 1.21 over 0.16, and that would give us, if we rearranged it, the one that we've got in the top. Okay, so that is not necessarily the most logical way of doing it, but it is the easiest way of doing it. And lastly, for 4D, we are reminded, we've already been told on the data sheet, that a fetus is small if it's below 10%. We are told that we are now at 30 weeks, so it's 2 weeks older, our fetus, so we'd expect it to have a different mean and a different standard deviation, both of which are arguably probably bigger. So calculate the standard deviation. So we do not know our standard deviation, so we want to know what the largest small fetus would be. So we're told the largest small is this in kilograms, and we want it to the nearest gram. So K is 1,000, so we need it to the nearest 0. So we've got tens, hundreds, thousands. So we need it to the nearest 1,000. So 3 decimal places. So, 4. Okay, so if I chuck that under there for a moment, it's probably... Right, so if we fold that there, then we can sort that. So, 4D. So we know that our mean is 1.559. We know that our standard deviation is what we're calculating. We know that our probability is 10%, which is 0.1. If we secretly put that in as 0.10, it's not actually an issue. And we know the value in context because we have a baby at 1294 kilograms. So, what we're going to need to do is a little bit weird. Because we need to calculate Z, and Z happens with a mean and a standard deviation of 0 and 1. So we've got a mean of 1 and a standard deviation of 0 gives us a value of Z. And it will have the same probability. So what we can do is we can use an inverse normal, and we are looking at below, so it's going to be less than. So the probability that Z is less than or equal to little z, that we don't know yet, equals 0.1. So on a calculator, we've got an area of 0.1. We've got a tail because we'd be looking at this bit. Our tail is going this way to the left. And we've got our mean and standard deviation as 0 and 1. So what we find is that Z is equal to minus 1.28. So we've got our value of Z. Our equation for Z is Z equals X minus mu over sigma. So minus 1.28 equals 1.294 minus the mean, so minus mu over sigma, which is the thing we don't know. So if we rearrange that, we get sigma equals missed. So if we times both sides by sigma and then we divide by this, what we end up with is on the top of our fraction 1.294 minus 1.559. On the bottom of our fraction we've got minus 1.28. So sigma equals 0. And we were told to do it the nearest gram, or 3 decimal places, so that should be 0.07, and that is in kilograms.